It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are going to look at Young's equation to determine the wavelength of light as it travels through the double slit. So let's just look at the equation, define the variables, and do a practice problem together. The equation is lambda equals x times d over L. Lambda we know is a wavelength and its units are meters. X is the distance between the first or center bright spot and the next bright spot, so the one right after it. And since it's distance, its units are meters. D is the distance between the two slits. Its units are also in meters. And then lastly, L is the distance from the slits to the screen. So the distance from the slits to the screen. That's where the light is hitting the wall. So let's look at an example together, and I'll show you a video of a laser going through the double slits. Oh, geez. Sorry. Didn't think you were watching. Well, I guess I'll do some physics. So what we're going to do is determine the wavelength of the green laser pointer using the double slit experiment or Young's equation. So if we could shine the green laser pointer through the double slits, and what we want to do is measure the distance between the first bright spot and the next one. If we do that, we're going to get about 51 centimeters or 0.51 meters. And we need to know the length from the double slit to the wall. That's 3.01 meters. And finally, the distance between each slit is 3.3 times 10 to the negative 6 meters. So let's calculate the wavelength and see if it matches up with the accepted value of the green laser. Sorry about my cat in the video, but let's get down to the measurements that we took. So in that video, the length measured between the double slits in the wall was 3.01 meters. The distance between the two slits was 3.3 times 10 to the negative 6 meters. And the approximate distance between the first bright spot and the next one was 0.51 meters. And what we wanted to do was calculate the wavelength of that green light to see if our measurements were accurate. So we'll start with Young's equation, lambda equals xd over L, and just plug and chug from here. So lambda is 0.51 meters times 3.31 times 10 to the negative 6 meters, all over 3.01 meters. We plug and chug, and in our calculators we get 5.59 times 10 to the negative 7 meters. Now when we're dealing with light, we technically write this as 10 to the negative 9th or nanometers. So this is also 559 times 10 to the negative 9 meters, or 559 nanometers, where 1 nanometer is 10 to the negative 9th meters. If we look at our green pen, on it, or green laser pen, on it, it gives us the given wavelength, and the accepted wavelength, so I'll say lambda accepted, is 532 nanometers. So we were only off by 27 nanometers, which is really close given it's very difficult to measure the distance between the two bright spots, as well as how far away we are from the wall. Hope you found this video useful. If you did, please like and subscribe, and I'll see you next time. See ya!